Good afternoon and welcome to the last day of the conference. Nuria, do you want to make any announcements before we start, or shall we start with the talk?
Afterwards, after Artur's talk.
Great. So it's a great pleasure to introduce Artur Nicolau from the University Autònoma of Barcelona. Do you have slides to share, Artur?
Yes, I do. So let's see. Here it is. Can you see them?
No.
No?
No, you haven't shared your screen yet.
Okay. I'm sorry.
Yeah, it seems like you're sharing now.
No.
Diu que sí, eh? It says you are sharing your screen. So maybe you just have to switch on the...
The slides are not there yet.
Okay.
Abans funcionava, eh?
Sí, something happens. I'm sorry.
No problem. Tenim tot el dia per davant.
Okay, let's try now. Can you see them now?
No, we cannot.
Jesus.
We can see you're sharing your screen now. We can see, yeah. Yes, that's it. Perfect.
Okay,
perfect. Great. So Artur is going to talk about a central limit theorem for iterates of inner functions. Thank you very much.
So thanks a lot, and sorry for this waiting. So, well, first, instead of starting the talk, I thought that I should mention that today is, well, a special day. It's April 23rd. So it's one of the most important days of the year in Catalonia. It's Sant Jordi, Sant George. So here I have, hope you see them, a couple of images of St. George, an ancient one and a, well, more modern one. And well, St. George is the patron of Catalonia. So, but it's a very important day, not only for that, but because it's a day of the books and roses in Catalonia. So let me explain that to you. This is a long standing tradition, and in every city, every village, even in every small village in Catalonia, books and roses are offered in the streets. So everyone go for a walk in the streets and tries to find the most interesting book, the most beautiful rose, and to give them to relatives, husbands, wives, daughters, sons, friends. So there is an incredible amount of roses and books which go from one person to another. So I thought I should also give you a present, but well, well, after some thinking, I thought that maybe you would like to be exposed to the Catalan language. So I chose a short part of a long poem by one of the national Catalan poets, Joan Maragall. And so here it goes. I will not translate it. So it's, I just want you to hear some Catalan. So it says, la diada de Sant Jordi és diada assenyalada per les flors que hi ha al mercat I l'olor que em fan els aires. And that's it. So this is the end of the present, okay? So, well, that was the hard part of the talk. The rest should be easy for me, at least. Okay, so let's go to mathematics, okay? Can you still hear me?
Yes, yes, we can.
Perfectament. Gracias.
So this is my title, and this what I will present is a joint work with Odi Solé. I have a picture of both here. Odi is the young one, the one still with some hair, and he's now a postdoc in Würzburg in Germany, working with Stephanie Peter-Michel. Okay, so the plan is to talk about inner functions. So inner functions have already appeared in several of the talks. The talk by the chairman today, Basso, the talk also by Christoph Baranski, and some other talks. So, but I will recall the definition. So an analytic mapping from the disk into itself is called inner. So here I have the disk. So this is the disk, and this is the analytic mapping. So it's called inner if the disk is mapped into itself. And it has this, this extremal property. The radial limits that you see here are of modulus 1 at almost every point in the circle. So roughly speaking, this means that the image of the unit circle, this should be understood in terms of radial limits, is included into the unit circle. Okay. So examples of inner functions, well, the most elementary examples are just finite Blaschke products. So finite products of disk automorphism. But of course, as you know, there are also more complicated inner functions. So for instance, infinite Blaschke products or something called singular inner functions. But even if you are not familiar with this, do not worry, because you could have this example in mind, and this will be enough for the talk today to have this example in mind. But the results hold for any inner function. So what we'll be interested is on the behavior of the inner function as a map from the unit circle into itself here, right? So this should be understood, as I said, in terms of radial limits. So this is defined as in terms of the radial limits. And these radial limits are only defined almost everywhere. So except for a set of Lebesgue measure 0. So this means that this mapping is only defined almost everywhere. And I should say that for a general inner function, this mapping could be highly discontinuous. So for instance, there are inner functions for which this mapping is discontinuous at every point of the circle. There are even inner functions for which the image of any arc is the whole unit circle. So it's far from being continuous, right? This mapping is just a mapping from the circle into itself, defined almost everywhere. And here are my notations. The nth iterate will be denoted as usual as f to the power n, and m will be normalized Lebesgue measure in the unit circle. And if I had to give the talk in a couple of sentences, I would say that the main message of the talk is that these iterates behave as independent random variables. And actually, what we are going to do is to present a central limit theorem for these iterates. Right? So, so since we are going to talk about CLT, let me recall that for you. So here is the central limit theorem, the most classical version, well, a classical version of it. So assume that you have real, independent, and identically distributed random variables, which are centered, and whose variance is sigma squared. Then the central limit theorem says that the sum, when conveniently normalized, tends in distribution to a standard normal variable. So this means this convergence in distribution, as you know, this means that for any, here k is any interval. So for any interval k in the real line, the probability of the normalized sum to be in this interval is given, well, tends, when n tends to infinity, is given by the Gaussian measure of the interval. Okay, so as I said, the plan is to talk about central limit theorem for inner functions. And actually, one difficulty is that in the context of inner functions, independence, the assumption of independence is not really present. But this already happens in other contexts. And actually, our work is inspired by an old result by Zalem and Zygmunt, who proved a central limit theorem for lacunary series. So let me state that. So first, the definition of a lacunary series. A lacunary series is a power series where the powers which are present in the power series are only ones which correspond to powers which grow exponentially fast. Okay? So most of the powers in the power series correspond to coefficients which vanish. And the only ones which are present are the ones which satisfy this condition. So for instance, typical example would be nk to be 2 to the power k. Okay? So in that case, only the powers which are powers of 2 would be present in the power series. Okay, and then again, what happens is that in some sense, the philosophy is that these monomials behave as independent random variables. And this makes a lot of sense, right? Because even if you know the first k monomials, you have some information on the first k monomials, since the powers grow exponentially fast, even if you have some information on the first k monomials, not too much can be said about the next monomial, right? Just because it's too large compared with the previous ones. And actually, this idea, I guess, was exploited by Zalem and Zygmunt, and also previously by Paley and Zygmunt. And the result here is a result by Paley and Zygmunt in the 30s. So very old result. It says the following. It says that if you have a lacunary series, then the three conditions below are equivalent. Either the series converges at almost every point is equivalent to the fact that the series converges at a set of positive measure, and this is equivalent to the fact that the coefficients are square summable. So in other words, if you want, you have here two possibilities. If the sum of the coefficient, if the coefficients are square summable, then the series converges at almost every point. While if the series of coefficients is not a square summable, then the series diverges at almost every point. So it's in a sense like a 0-1 law, right? Either the behavior is very good or it's very bad. And this really depends on how the coefficients decay to zero, right? If they are pretty small, then the series converges. If not, then the series diverges at almost every point. So after that, Zygmunt and Salem in the 40s proved a version of the central limit theorem. So here it goes. Here is the central limit theorem of Salem and Zygmunt for lacunary series. So it's very nice. It says the following. Assume that the series of coefficients is not square summable. Then we already know, since it's not square summable, then we already know that this sum, well, I'm sorry, this sum diverges at almost every point. Okay, this is what I already stated in the previous screen. So the series diverges at almost every point. But then you can ask, well, even if it diverges, how do the partial sums distribute their values? And Salem and Zygmunt found that they distribute their values according to a normal distribution, to a Gaussian distribution. So let me read the result. Assume that the series of coefficients diverges, and assume this technical condition. This sigma n is the sum of the partial sum of the square of the coefficient. So this is the variance, right? This plays the role of the variance. So this is the L2 norm of the partial sum. So assume that an divided by sigma n tends to 0. So this means that in this sum, an individual term is not relevant, right? The partial sum tends to infinity due to several elements, right? Not for an individual element. Then what happens is that under this condition, then again, the partial sum, when conveniently normalized, turns in distribution to in this case to a complex normal variable. So this means, I wrote here, this means that the measure, so if you are given say a disk, so K is going to be a disk here now. If you are given a disk, then you look to the measure of points where the partial sum, when conveniently normalized, belongs to this disk. When n tends to infinity, this tends to the Gaussian measure of the disk. Okay? So it's very nice, I guess. It says that even if the series diverges, it distributes, the partial sums distribute their values according to a complex Gaussian. Okay, and I guess they also like, I guess that also Salem and Zygmunt like the result a lot because they proved many different variants. They proved similar results for trigonometric series, or also in other contexts. And in particular, I wanted to mention that they proved a local version of this result. So this means that they proved the following. They proved that even if you're given a set E in the circle, any measurable set of positive Lebesgue measure, it turns out that there is also a central limit theorem in this set E. So it's also true that when you look to the characteristic function, and you divide by the measure of E, this also tends to a normal Gaussian, to a normal complex variable. Or if you want, in other words, here in this statement, if you replace here the unit circle by the length, by the points in E, this is still true, okay? So this is still true, right? So it's not only that you have a central limit theorem in the whole circle, but you have a central limit theorem even in any fixed measurable subset of the circle. as I said, they proved many variants. Here is another one which I want to mention.
Artur, may I have a question?
Please. Please.
Sorry, this, so the AN, the sequence that or the series that you are taking at the beginning is any series. So it's not lacunary or nothing. It's just
no, no. The series of the AKs are any kind of coefficients, but observe that here only are present a lacunary series, right? A lacunary series of power, a lacunary sequence of powers. Okay? So this is a lacunary series.
Ah, so you start with a series and then you take any possible lacunary series according to this AN. Ah, okay, sorry.
Yes, yes.
Okay.
And now I wanted to say something about what they also proved a tail central limit theorem. So this is also, again, very nice. So let me just try to explain it. So assume now that instead of that, assume that you have a series of coefficients which are square summable. Okay? Then, well, if they are square summable, we know that the lacunary series converges at almost every point. So we know that this converges almost everywhere, right? But again, you can say, okay, even if it converges almost everywhere, you can ask yourself, well, how do the tails distribute their values? So, and again, the tails distribute their values according to a complex normal variable. So in that case, what you need to do is you need to consider the variance of the tail. And then instead of this, you would consider here the sum for k bigger than n. And here you will replace this variance by the variance star, okay? And the result still will be still true. So it's not only that the partial sums distribute their values as a complex Gaussian, but in the case of convergence, even the tails distribute their values according to a complex normal variable. Okay? So as I said, this was the main inspiration of our work. So let's return now to the original setting of inner functions. Okay, and I guess I should mention, something about the dynamics of an inner function. This is something which has been extensively studied. So, the first thing is that we will always be talking about inner functions fixed in the origin. And in that case, as you know, the Nicolau theorem says that if you have an inner function fixed in the origin, the iterates converge uniformly on complex to the origin. So the origin acts as an attracting fixed point. And actually, it's not very surprising, right, in this context, because the derivative at the origin by Schwarz's lemma is smaller than 1. So you would expect that. But as I said, our main interest would be the behavior of the inner function as a map from the circle into itself. As this map, which is only defined at almost every point. And this has already been studied by many persons. There are many things are known, this mapping. So I will fix attention now to inner functions which map the origin into itself. So then the mapping is, this mapping from the circle into itself is known to be ergodic, exact, it's mixing, we know when it's recurrent, and so we have many information. So in particular, it's ergodic, and here I have just stated the ergodic theorem for you, right? These are, I call it this law of large numbers. So you have an inner function fixed in the origin. Then here you have the temporal means. So it converges to the spatial means, and the spatial mean is 0 because the function fixes the origin. So this means that for almost every point, if you look to the orbits, so in some sense, the orbits, for almost every point, the orbits are very well very well distributed, right? In such a way that when you take the mean, this tends to 0. Okay, so, but what we will be interested in is the central limit theorem. So let me go for that. So in the central limit theorem, you have two main assumptions, right? One is independence, and the other is the fact that the variables should be, well, some assumption on the distribution of the variables. So in our context, we have a good and a bad new. So let's start by the bad new. The bad new is this one, right? That the iterates are not going to be independent in any sense, right? Because actually I cannot imagine anything less independent than the iterates, right? The n+1 iterate depends completely on the nth iterate. Okay, so this assumption is far from being satisfied. And this is the bad new. And this is actually, well, the most difficult part in our work. But there is a good news. And the good news is that the maps are identically distributed. And this is given by a result called Lefner's lemma. This already appeared in Phil's lecture the first day. But let me recall that for you. So you have here an inner function. So imagine you have a set E here, right? So the Lefner's lemma says that if an inner function fixes the origin, then the preimage can be very complicated, topologically very complicated. It could have many different components, but it is still true that the measure of the set is equal to the measure of the preimage. So in other words, the Lebesgue measure is invariant. This is actually easy to prove, but instead of proving it, I thought that it would be more nice to give you an example. And the example is, well, the easiest one, right, is z to the n. Okay, so here imagine you have z to the n as the inner function. Then imagine you have a set E here, say an arc of length delta. Then, of course, the preimage consists of tiny arcs. This would be the preimage of this arc by z to the n. And each tiny arc would have length delta divided by n, right? Since you have n arcs, this condition holds, right? So in that case, for this inner function, this is completely trivial. So another way of stating that is in terms of integrals, right? If you want to verify this identity for any function, integrable function, you can, of course, assume that your function is the characteristic function by linearity, the characteristic function of a set. And if G is the characteristic function of a set, this is precisely Lefner's lemma, right? This would be just the measure, this would be the measure of the set. This would be the measure of the set, and this would be the measure of the preimage. And this easy observation is already useful because it will allow us to compute the variance in our context. So let me do that, okay? So this will be just a fun computation, okay? So let's start with this. Let's start with two indexes, two positive integers n and k, and let's compute this integral, okay? So you have the nth iterate, conjugate, and then you have the kth iterate. Then what you do is you apply this formula, right? You can decompose by f, right? So you apply this formula to f to the n, so you decompose with f to the n, and you arrive to this expression here, okay? But of course, in this expression, you just apply Cauchy's formula. So this is, by Cauchy's formula, this is just the derivative of this function at the origin. And remember that f was an inner function fixed in the origin. So this is just by chain rule, This is just this expression here. So, and as I said, this allows us to compute the variance, right? Because this would be the variance, yeah, the L2 norm of the partial sum. And then what we do to compute that is, well, we just expand, right? Instead of this, we just expand. And then I guess you have something like this. Yeah, something like that. And remember that f was a linear function. So since f was a linear function and we are integrating over the circle, this is just 1. So this we can forget. Then, well, the thing is now very easy, right? We need to integrate this, but we already integrated these guys. And we were getting this derivative to the power k minus n. So this is what we get at the end, okay? So this means that we have here, if you want, when you compute the variance, you have 2 terms, this one and this one, right? And remember that f was a linear function fixed in the origin. So f prime of 0 is smaller than 1 in modulus. So it's not hard to believe that what happens is that this second term will be absorbed by the first one, just because this is going to be just because this is smaller than 1. This requires some explanation, but I guess it's easy to believe. And then, well, we arrive to the fact that the variance is comparable to the L2, to the partial sum of the square of the coefficients, okay? And actually, more is true, right? Here it's, I have stated here the thing in L2, the convergence in L2, but it also holds almost everywhere. So it turns out that this converges if and only if this sum converges at almost every point in the circle. Okay, so as in the case of lacunary series, the convergence, the L2 convergence of the coefficients is equivalent to the pointwise convergence. And then we can ask the same thing. So assume that the coefficients are not square summable. So if the coefficients are not square summable, the series diverges at almost every point again. Yeah, this is still true, right? I should mention that. If the series diverges, then this diverges at almost every point. So it's at almost every point. So it's very similar to what happened with lacunary series. So what I was saying is that, well, now we can ask, well, if the series diverges, okay, it diverges at almost every point, but how do the partial sum distribute their values? And now this is our central limit theorem. So this is the main result of the 12th. So let me call sigma n to the variance. I already computed in the previous screen. So this was this large expression. And here is the result. Assume that you have an inner function fixing the origin, which is not a rotation. And assume that you have coefficients which are bounded and which are not square summable. So as I said, this means that the sum, the linear combinations with these coefficients an of the iterates diverges at almost every point. So this series here diverges at almost every point. And then you can ask, okay, this diverges at almost every point. How do they distribute their values? Well, when the result says that when conveniently normalized by the variance we have written here, then the series, the normalized partial sum converges in distribution to a complex Gaussian again. So this is the result. And I wanted to make a few remarks. Well, the first remark is that, well, as you see, no lacunarity assumption is needed here, right? This is the whole sequence of iterates. The result would be, I mean, the proof would be much more easy if we would restrict attention to a sequence of to a lacunary sequence of iterates. But here is the whole sequence of iterates. Well, the second thing is that assume now that if you assume, instead of assuming that the sum of the coefficients is infinite, you assume that the sum of coefficients is finite, then, as I said, this series converges at almost every point. But again, you can ask, well, what about the distribution of the tails? And here still we can give a version of the central limit theorem for tails. Okay? I'm not going to state it, but I guess you can imagine how it would be. And here is, so these are positive things. Here is a negative thing. The negative thing is that we have no local versions of the result. So this means, well, we have no local version means that we do not know how to prove a local version. So this means that if you are given a set of positive measure of the circle, I guess it would be natural to ask if this still tends to a complex Gaussian, okay? And well, we don't know, as I said, we do not know if this is true or not. So, and well, the main obstacle is that, as you will see, our arguments are some of our arguments are complex variable arguments, in the sense that we use that certain integrals vanish. This magical thing of complex analysis, that cancellation is extremely present, right? That certain integrals vanish. And the integrals we have are over the whole unit circle, and the integrals over the whole unit circle vanish. If instead of the whole unit circle, we have a subset of the unit circle, we could prove that the integrals are small. But if they do not vanish, we do not know how to continue. So it's a matter of our arguments, which do not seem to apply to prove these local versions. So, okay. So next remark is that, well, there is a particular case which I should mention, which is the case of having all coefficients equal to 1. Right? If all coefficients are equal to 1, this is of course an important case because these are just ergodic sums, right? And in that case, if all coefficients are equal to 1, well, the variance is very easy, right? To compute. This would be just n, and this here you will have just a geometric series that you compute, and you arrive at the sequence that the variance is just n times sigma squared, being sigma squared this nice expression. And in that case, we show that our result says that this tends to these ergodic sums tends to a complex Gaussian, center complex Gaussian of variance sigma squared. Okay, so this is the result. And in the rest of the talk, I would like to say a few words about the proof. And well, the proof is long, and at least for us, it was difficult. And it contains, what I have done is, instead of, I have just extracted two main ingredients in the proof. And here are the two main ingredients, the two main estimates, okay? So let's talk about the first one. So in the first one, we have, as you see here, two sets of indexes, A and B. So A and B are subsets of positive integers. And here, what I want to say is that the integers in A, so here we have 1, 2. Well, the integers in A are at the left of the integers in B. Okay, so this is the situation, right? Then the formula, it says the following, that if I call psi sub A the partial sum corresponding to the indexes in A, then it happens that the integral of the modulus of the square of the product is the product of the integrals. This is a fantastic formula, right? Because it says in you that the integral of the product is the product of the integrals. So it's quite remarkable. And I guess that if I was looking to this formula, the first time I would say, okay, this formula should be true because these two guys, the square of the modulus of psi sub A and the square of the modulus of psi sub B should be independent. Because, well, if they are independent, of course, the expected value of the product is the product of the expected values. But the main point is that they are not independent, right? They are completely dependent in a sense, right? Because they come from the same inner function which are iterated, right? So they are not independent. But still, the integral of the product is the product of the integrals. So this is the first main result where we use in the proof. And here is the second one. In the second one, let me use this notation. So f to a negative power would mean just the nth iterate and then a complex conjugate. So the complex conjugate of the nth iterate. So the second main estimate says the following. Assume that you have a sequence of positive integers, an increasing sequence of positive integers, and say that each integer is q units apart from the previous one, okay? And q is going to be a large number. Epsilon j will denote pluses or minus ones. Then the result says that when you integrate over the whole unit circle, the product of, let's look to this product. This is just the product of iterates, or maybe if epsilon j is -1, complex conjugates of iterates. So you are multiplying iterates and complex conjugate of iterates. So this gives you a bound, okay? And actually, we are going to use this when q is much more bigger than k. So this means that this part here is negligible because q is going to be much more bigger than k. And remember, since f was fixed in the origin, the derivative at the origin was smaller than 1. So this gives you that this decays exponentially. And of course, this is relevant because this, what you have in the left is just like a correlation, a higher order correlation of the iterates. So this is telling you that the higher order correlations of the iterates decay exponentially fast. And this is something which is relevant in the central limit theory. Okay, so now my plan is, well, the two things, the two results I wanted to say is that the two results are correspond to integrals over the whole unit circle, right? If instead of the unit circle, you have the integral over the set, a set E in the unit circle, then the results are no longer true. So this is due to the fact, as I said, that the proof of these things use really complex analysis techniques. So, and actually the proof of both results depends on a very nice tool, which I want to present, which is Alexandrov Clark measures. So let me present that for you. So assume that you have an analytic mapping from the disk into itself. Here it's F. And then you compose it with this mapping, which maps the unit disk into the right half plane, okay? Then what happens is that, of course, the composition has positive real part. So it's the Poisson, as we saw in Phil's talk, this is just the Poisson integral of a positive measure, or in other words, the Herglotz integral of a positive measure. So these mu alpha are called the Alexandrov Clark measures of the function f. And these measures were introduced by Clark in the 70s in relation to problems in operator theory. but they have been studied by many other researchers as Achen, Clark, Poltoraski, Sarason, Saxman, and many others who discovered their main properties. Let me mention here a couple of things. The first one is the fact that the function, the original function here is inner, so maps the circle into itself, if and only if these measures are singular. So they are concentrated on a set of Lebesgue measure 0. And the second thing is that the places where they are concentrated precisely in the preimage of the set of the point alpha. So this means the following, that you have here your inner function, you have here your point alpha, then you have a measure which is concentrated in the preimage of the point alpha. Here is the measure mu alpha, concentrated here. Of course, if you had a different point beta, then you would have a different preimage. And then you would have a different measure, which is concentrated on this set, and it's called mu beta, okay? And now here is the main point. The main point is this nice result by Alexandrov, which says, when you average all these measures, all these Alexandrov Clark measures, you recover the Lebesgue measure. Or in other words, if you're going to integrate a function against Lebesgue measure, you can do the following. You can do it in the following way. You integrate against Alexandrov Clark measures, and then you average the result with respect to these integrals. Oh, and this is what it's really used in the proof of our result. So let me just mention the proof of this first identity. The second result is much more difficult to prove, but this, I guess it can be easily explained. Okay, so this was the first result, that the integral of the product was the product of integrals. So how do we act? So I guess that we act in the most naive way. So we want to prove that this integral is the product of integrals. So what we do is we just expand the modulus square as it is here, and expand the modulus square of the corresponding sum for B. And then you multiply. And when you multiply, you arrive to linear combinations of these guys. And these guys correspond to indexes N and J, which are in the first set A, and K and L, which are in the second set B. So in order to prove the theorem, I guess it's not hard to believe that you need to prove this, that the integral of this product is the product of the two integrals. But remember, these two were already computed. We know that this is this, and we know that this is that, okay? This we already computed. So we need to compute, we just need to compute this. So let's go. So to compute this, what we do is the following. We first decompose with f to the n, okay? So we can, this is because of the invariance of Lebesgue measure. So we decompose with f to the n, and we arrive to this expression. And now we apply Alexandrov's disintegration theorem, which says that the Lebesgue measure is just the integral of the Alexandrov Clark measures, corresponding to, in that case, will be corresponding to this iterate, okay? This is very interesting because corresponding to this integrate, this means, to this iterate, it means that the measure is concentrated in this set, in the preimage of the point alpha. So this means that when we integrate over mu alpha, this is equal to alpha, and this will be equal to fk minus j, fk minus j of alpha, and here fl minus j of alpha. So you arrive to this expression. Here you have the double integral, but observe that here, the only dependence on z is in here, okay? So you have to compute now the moment of this measure, mu alpha, and you had this formula. So now it's easy. From this formula, you can easily compute the moment, actually every moment of the measure mu alpha is present in this formula. So in particular, you have this expression. And here is the nice thing, that you get here alpha bar, right? And this is the cancellation, the incredible cancellation. You have alpha bar, and here you have alpha. And you are in the unit circle, so you have the modulus square, which is 1. So this means that the alphas disappear here. And then what you have is, as I said, just this sum, and then the previous integral that we already knew how to compute. So this would give you the proof of the first identity. The second, as I said, is harder to prove. And once these two identities are proved, well, still some work is required to prove the central limit theorem. But these are the two main ingredients. So I guess that I will skip the final, and I just thank you for the kind words, the kind attention, and I wish you a Feliz San Jordi. So thanks a lot.
Thank you very much, Artur, for a great talk. Are there any questions or comments for Artur?